Hello everyone, this is Zhonghua Wang from Institute of Software Chinese Academy of Sciences. I'm here to give the video of our research track paper Improving NLSAT for Nonlinear Real Arithmetic. We introduced a new solver called Clause SMT to tackle the problem of SMT-QFNRA. The problem of SMT-QFNRA is that given a Boolean combination of polynomial constraints, we want to determine that whether the formula is satisfiable under any assignment or is unsatisfiable. Given the two circles in the picture, the satisfiable space is pictured as the blue area, and this constraint can be satisfied under the assignment that x equals to 0 and y equals to 1. Previously, there is an algorithm called NLSAT or ASE' framework. NLSAT is a concrete implementation in the Z3 solver. It searches the solution space by removing conflict spaces and learning new lemma. For example, given a formula f, we first update the feasible set according to the second clause, and that we get the feasible set that x must be less than or equal to 0. Then we get an arithmetic value for the variable x. For example, we get that x equals to -10. Then we update the first the value of the feasible set according to the clause 1, because x is assigned and this clause is univariate to the arithmetic variable y. We find that the feasible set of y is empty, so that this clause is conflict. We use a CD-based explanation to generate a new lemma, and found that x must be greater or equal to -2. Then we get a new value and use the semantic decision to determine the value. So for example, we get the value to be -1. Then we again update the feasible set of the first value, and then we choose the final assignment for y. Then we determine that this formula is satisfiable under the assignment x equals to -1 and y equals to 0. However, ASE' is short-sighted when facing multiple literal clauses. For example, in the second clause, x equals or less than 0 or x is greater or equal to 6. We must first decide the literal. For example, we decide the second literal to be true, and then we use that literal to update the feasible set and get a value for the variable x. We found that the first clause is conflict. However, this could be true if we decide the first literal. This example tells us that the literal decision strategy is very important. Here we systematically analyze the conflict types in the ASE' algorithm. The first type of conflict is called semantic-based conflict. For example, given the formula f, if we assume that x is equal to 0, this could be true because there is no clause that narrows the x feasible set. And then we detect conflict that the original clauses narrows y feasible set to be empty, so that we must change the value of x. This is caused by an incorrect semantic decision and could not be foreseen at the time of decision. It must be resolved later by a new generated lemma. The second type of conflict is called literal decision. It happens when deciding a wrong literal. For example, given these three clauses, if we combine clause 1, clause 2 to be a new formula, then we must decide the first literal of clause 1. If we combine clause 1 and clause 3 to be a new formula, this is only satisfiable under the literal decision of the second literal when processing the first clause. In the picture, we find that the red area only have intersection with the class 2 line, and the blue area only has the intersection with the line 3. So that the question is, how do we dynamically detect literals? Which literal should we branch or decide? This can be foreseeable at the time of decision using some interval view, and could be avoided given a proper literal decision strategy. We categorize these cases into two cases. Example 5 is a past case that the feasible set of a variable is not empty, so that we can choose, for example, the literal in the green boxes to decide some literal to avoid that type of conflicts. Example 6 cannot be avoided conflicts under any literal combination. The first step is to compute the clause level feasible set. We compute this by the first. For each clause, we use the union to compute the feasible set of each literal, and then we intersect them into the overall feasible set of the arithmetic variable. Then we select a weakness within the interval set, for example, x equals to 3 within the interval 2 to 4. Then any literal satisfiable under x equals to 3 are decided. For example, in the example 5, those green boxes. So here is a formal algorithm of our previous decided method. Algorithm 4 tackles special cases when we incrementally compute a new generated lemma. So we update the feasible set of a given arithmetic variable and compute the previous interval set computation and decide a new literal combination. The second part of our video is to introduce a new propagation in NLSAT. Here we look back to propagation methods in NLSAT. The first one is about unit propagation borrowed from set solving. When the literal that x is equals or less than 0 is decided to be false, then the sum of square x plus y must be less than 4, must be true. The second type is about real propagation. For example, the square of x is less than 0. This must be false under the real arithmetic. However, both propagation methods remain confined to the literal level, I mean to assign some literal's value to be true or false or undefined, and missing the guidance of our arithmetic semantics. Here we introduce a new kind of propagation called clause level propagation. We know that in set solving, propagation are used to deduce some new assignment or to detect a conflict clause. This only happens after a new assignment. This new assignment could be decision or the deduction of a unit clause. We define the clause level propagation to be that under a new arithmetic assignment, for example, x equals to 0, we quickly update the feasible set of another variable in a unit variate clause. And this can be categorized into 3 cases. The block case, that the feasible set is empty. The fixed case, that the feasible set only contains one real number. And other cases, for example, the first one. We introduce a new branching heuristic that we first prioritize blocked variables. This could guide our algorithm to the conflict cases so that we can first focus on how to fixing the conflict rather than decide some other values of some unnecessary variables. Next, we consider fixed cases so that we can quickly deduce the values of those variables. We show the evaluation of our solver called cloud SMT in the table in the in the last column of this table. One can see that we beat all other mainstream solvers on the certifiable instances. And our solver ranks the second overall in the QFNRA SMT Lab benchmark. So this paper can be updated the NLSAT algorithm in the, I think, 4 ideas. The first one is about a new literal decision method look-ahead mechanism. The second one is that we introduce a new propagation method called cloud level propagation. And then we use that propagation to design a new branching heuristic to improve the search space of the algorithm. And currently, it is the sole solver for certifiable instances under the QFNRA benchmarks. Thank you.